Welcome to another full of learning discussion, everyone. Our lesson for today is about curve fitting and interpolation. Our learning objective for this lesson are distinguish and connect discrete data points to get reasonable data point between the given point. Determine the curve that could best indicate the trend of a given set of data. Perform interpolation of polynomial. Perform the conventional quadratic and cubic spline interpolation. Curve fitting. Data is often given for discrete values along a continuum. However, you may require estimates at points between the discrete values. There are techniques to fit curves to such data to obtain intermediate estimate. One way to do this is to compute values of the function at a number of discrete values along the range of interest. Then, a simpler function may be derived to fit these values. Both of these applications are known as curve fitting. Non-computer method for curve fitting. The simplest method for fitting a curve to data is to plot the points and then sketch a line that visually conforms to the data. Although this is a valid option when quick estimates are required, the results are dependent on the subjective viewpoint of the person sketching the curve. For example, in figure PT 5.1 shows sketches developed from the same set of data by three engineers. The first did not attempt to connect the points but rather characterized the general upward trend of the data with a straight line as shown in figure A. The second engineer used a straight line segment or linear interpolation to connect the points as shown in figure B. This is very common practice in engineering if the values are truly close to being linear or are spaced closely. Such an approximation provides estimates that are adequate for many engineering calculations. However, where the underlying relationship is highly curvilinear, or the data is widely spaced, significant errors can be introduced by such linear interpolation. The third engineer used curve to try to capture meandering suggested by the data as shown in figure C. And then a fourth and fifth engineer would likely develop alternative ways. Obviously, our goal here is to develop systematic and objective methods for the purpose of deriving such curves. Curve fitting and engineering practice. Although many widely used engineering properties have been tabulated, there are a great many more that are not available in this convenient form. Special cases and new problem contexts often require that you measure your own data and develop your own predictive relationships. Two types of application are generally encountered when fitting experimental data. Trend analysis represents the process of using the pattern of the data to make prediction. For cases where the data is measured with high precision, you might utilize interpolating polynomial. Imprecise data is often analyzed with least squares regression. So, trend analysis may be used to predict or forecast values of the dependent variable. This can involve extrapolation beyond the limits of the observed data or interpolation within the range of the data. All fields of engineering commonly involve problems of this type. A second engineering application of experimental curve fitting is hypothesis testing. Hypothesis testing is an engineering application of experimental curve fitting where an existing mathematical model is compared with measured data. If the model coefficients are unknown, it may be necessary to determine values that best fit the observed data. On the other hand, if estimates of the model coefficient are already available, it may be appropriate to compare predicted value of the model with observed values to test the adequacy of the model. Often, alternative models are compared and the best one is selected on the basis of empirical observation. In addition to the above engineering application, curve fitting is important in other numerical methods such as integration and the approximate solution of differential equations. Finally, curve fitting techniques can be used to derive simple functions to approximate complicated functions. So let's have a mathematical background. So we will have here a simple statistic. Suppose that in the course of an engineering study, several measurements were made of a particular quantity. So, for example, in table PT 5.1 contains 24 readings of the coefficient of thermal expansion of a structural steel. Taken at face value, the data provides a limited amount of information. That is that the value range from a minimum of 6.395 to a maximum of 6.775. Additional insight can be gained by summarizing the data in one or more well-known statistics that convey as much information information as possible about specific characteristics of the dataset. These descriptive statistics are most often selected to represent 1. The location of the center of the distribution of the data and the degree of the spread of the data. The common location statistic is the arithmetic mean. The arithmetic mean or the bar y of a sample is defined as the sum of the individual data points divided by the number of points as shown in this particular equation PT 5.1, where the summation and all the succeeding summation in this introduction is from I equals to 1 through n. The most common measure of the spread of a sample is the standard deviation about the mean. As shown in this particular equation, S sub y is equals to the square root of S sub t all over n minus 1, wherein S sub t is the total sum of the squares of the residuals between the data points and the mean. As shown in this equation, S sub t is equals to the summation of the difference y sub I minus the arithmetic mean squared. Thus, if the individual measurements are spread out widely around the mean, S sub t and consequently S sub y will be large. If they are grouped tightly, the standard deviation will be small. The spread can also be represented by the square of the standard deviation, which is called the variance. So, in the equation PT 5.4, variance or S sub y squared is equals to summation of the difference y sub I minus the arithmetic mean squared all over n minus 1. Or S sub y squared is equals to the summation of y sub I squared minus the squared of the summation y sub I over n all over n minus 1. A final statistic that has utility in quantifying the spread of the data is the coefficient of variation or CV, often multiplied by 100 so that it can express in the form of a percent. So as the equation PT 5.5, CV is equals to S sub y all over the arithmetic mean multiplied by 100%. For example 1, simple statistics. So problem statement, compute the mean, variance, standard deviation, and coefficient of variation for the data in table PT 5.1. Table PT 5.1 or the measurements of the coefficient of thermal expansion of structural steel is in this particular data set. So for the computation, so we will have here the readings of the coefficient of thermal expansion. The frequency and bounds are developed to construct the histogram in figure PT 5.2. So it will be represented in this particular tabulation. So we have here the I or all the data sets from the first to the last data point, and we have here the Y sub I or Y sub I are the measurements of the coefficient of thermal expansion of structural steel, squares of the difference of y sub I minus the arithmetic mean, the frequency, the lower bound, the upper bound, also known as the interval. So for this particular set, the solutions are data is added and the result are used to compute the arithmetic mean. So we have here the summation of y sub I all over the number of the data set. As in table PT 5.2, the sum of the squares of the residual is 0.217000, which can be used to compute the standard deviation. So we have here S sub y is square root of S sub t all over n minus 1. So it will be square root of 0.21700 all over 24 minus 1 equals to 0.097133. And the variance as represented by the equation PT 5.4 or simply the square of the standard deviation. So we will have here 0.009435. And the coefficient of variation in percent is S sub y or the standard deviation all over the arithmetic mean multiplied by 100%, which will have a value of 1.47%. Figure PT 5.2 is a histogram used to depict the distribution of data. As the number of data points increases, the histogram could approach the smooth bell-shaped curve called the normal distribution. Let's try using Excel applying simple statistics. So in continuation with our discussion, we're going to use Excel applying simple statistics. These are the given. We have here 24 data sets and we have here the value of y sub I. And y sub I are the measurements of the coefficient of thermal expansion of structural steel. So first, we're going to determine the summation of S sub t and the summation of y sub I. So first, let's find the summation of y sub I in order to find the arithmetic mean. And we have here n is n number from the values of I from 1 to 24. So this is n. So first, let's have the summation of y sub I. So sum, select all the data set, and we now have the summation of 158.41. Next, we're going to calculate the arithmetic mean. So the summation of y sub I all over n. So summation of y sub I all over n. And we can also calculate the arithmetic mean by finding the average of the data set. The average, select the data set, and we will also have the same result as the summation of y sub I all over n. And for the standard deviation, so we're going to find first the value of s sub t, and s sub t is the summation of y sub I minus the arithmetic mean squared. Y sub I minus the arithmetic mean raised to 2, so that is squared. So let's have here the dollar sign. So we didn't define the name for the arithmetic mean, so we can just simply use the dollar sign and simply apply all the equations, and that's when we're going to find the summation. So select all the data set, and we already have the value of 0.2176, and we will now be able to find the value of the standard deviation. So it will be square root, so SQRT. S sub t is the summation at square divided by n, so n24 minus 1. So we now have here the value of the standard deviation. And for the variance, so we also have here the summation, or simply square the standard deviation. So we're going to try the other formula in finding the variance. But in order to find the value of the variance, so we already have the summation of y. Now we're going to find the squared of the y sub I. So this will be the squared of the given data set, and it will be applied on all the data set given, and we're going to find the summation. So applying the formula, so it will be the summation of y sub I squared minus the squared of the summation divided by n all over n minus 1. So we will be able to find the same result of the value for variance. So we're now going to calculate the value of the coefficient of variation in percentage. So the coefficient of the variation is standard deviation divided by the arithmetic mean multiplied by 100. So we will have here the value of 1.47% as the coefficient of variation. So the individual data set can be grouped using the interval of the lower bound and the upper bound. So we will have here first, so for our lower bound, so we're going to use 6.36 as the lower bound, and for the upper bound, so let's have here an interval of 0.04. So we will have 6.4 as the upper bound. So in this particular interval, we're going to check how many set of data are in this particular interval. So we have here one data set, so only the 6.395 is within the interval of the upper bound and the lower bound of 6.4 and 6.36 respectively. So using the same bound and adding 0.04, so in this particular interval, so we're going to calculate how many data sets are within this particular interval. So 6.4 to 6.44. So in this particular data set, so we also have here one data set, so one frequency, and same process. So we have here 6.44 and 6.48. So in this particular data set, how many frequencies are within this particular data set? So we only have here 0 value within 6.44 to 6.48. So in order to avoid confusion, so we're going to move this in this particular location. So for the next data set, so we have here 6.48 and 6.52. So how many data set are within this particular interval? So we will have here 4 data set within this interval. So in order to avoid confusion, so let's put a color coding. For the next interval, we have here 2 data set. For the next data set, so we will have here 3 data set within this range. For the next interval, we have here 5 data set are within this particular interval. And then for the next interval, so we have 3 data set. And for the next interval, we have here 3 data set. And so we have here 1, and we also have here 1 data set. So this is the representation of the group data, and this is the representation of the individual data set. So in order to easily distinguish the frequencies of the given data set, we can apply the Excel function. So first, we have to distinguish the bins. So we started from the lower bound of 6.36 and with an interval of 0.04, let's say until 6.84, and see if this particular data set we have indicated will be shown in these particular bins and frequencies. And this will be important in graphing the histogram with its normal distribution curve. So we're going to select data and click the data analysis. If data analysis is not shown in your Excel, so like this one, so we're going to click file, click options, and click add-ins, and show the Excel add-ins, and click go, and simply click the analysis toolpath and click OK. So after that, it will show the data analysis. And so we're now be able to click the data analysis and click histogram, click OK, and the input range. So the input range here are the given data set. So we have here the data set, the values of Y, and the bin, and we will have here the output range. So the output range, so we're not going to have our output in the new data sheet or in the new workbook. So we're going to have it in this particular worksheet. So we're just going to select where do we want the result to be shown. So let's select R. And upon clicking OK, it will show all the bins and also the frequencies. So we don't have the value for 6.36, but we have from this particular 6.36 to 6.4, we have a frequency of 1, and 6.4 to 6.44, so we also have here 1. We don't have for 6.48. We have 4 for 6.52, and we have 2 for 6.56, 3, so on until we don't have the value for 6.84. So we already have here the bin and the frequency. So in order now to plot or to graphically shown in an histogram or in a normal distribution curve, so we're now going to select the bins and the frequency, insert, and the scatter. So we will have here the representation for the histogram, but this is not yet the represented histogram. So we're going to adjust. Let's adjust this data set. So let's indicate the major as 0.04 in order to distinguish based on our bin. And so let's enlarge this particular data set. So from this particular data set, change the chart title. So the measurement of coefficient of thermal expansion of structural steel. And we're going to add here, so chart design, add chart element, so error bars. So click on more error bars and click on the 3 bar. So we're going to click minus, no gap, and we're going to have the percentage in 100%. Let's change the bound. So we have here the minimum of 6.36 and the maximum of 6.84. So these are the data set, and you will notice here that we have here the dots and it has a line. So this is now the representation, and you will notice the histogram or the bar graph for the histogram of the measurement of coefficient of thermal expansion of structural steel has thin thickness. So we're going to double click this data. So we will be put back on the format error bars and the change data. So we change it to minus and the no cap and the 100%. Simply select the line and fill. So from this particular line, so we're going to change the width. So you will notice it only has 0.75, or we're going to try 40. So this is the representation of histogram, and we already have this histogram. So now we're going to have this line here as no line, and the marker, so no border, no fill, and none, to hide the dot. And we already have here the histogram, or simply the bar graph of represented group data. So from this particular data, so we're now going to graph the distribution or the normal distribution curve of this particular data set. So the step 1 is simply finding the mean and the standard deviation. So this is the step 1 in plotting the normal distribution curve. For step number 2, using z-score of the normal distribution table from negative 3.9, it has an interval of 0.1 until 3.9. So we are just following the solution process. So if you recall the normal distribution in your previous subject, so I think you already discussed this because this is only a mathematical background. So this is not the focus of our discussion. So continuing, so this is the step number 2. For step number 3, so we're now going to calculate the value of x. And for step 4, we're going to calculate the value of y. And we all know that in order to calculate the value of x, so we have here this particular formula. X is simply equal or approximately equal to the arithmetic mean minus the standard deviation multiplied by the z-score. So this will be the arithmetic mean minus the standard deviation multiplied by the z-score. So we're going to use the dollar sign in order not to change the selected value for mean and the standard deviation. And these are the value of our x. And now we're going to calculate for the value of y. So we're not going to calculate manually using the formula. What we're going to do is to apply the Excel function. So this will be the normal distribution or norm disk, and select the value of x, the value of mean, the value of the standard deviation, and we're not going to use the cumulative distribution function. So we're going to use the probability mass function. So it will have a bell-shaped plot. So we're going to type false, and we will have here this particular value. But we have here the 0.04 and we have only a 24 data set. So we're going to multiply this by 24 and 0.04. So we're going to put dollar sign on the mean and the standard deviation data and apply the same formula to all the values, and we're now be able to plot. So we can now plot the data set by simply select the chart, select a data, and add. So we're going to have here the normal distribution curve. So for the x value, so these are the x value, and for the y value, and click OK. And in this particular graph, so we're going to change the chart representation. So marami tayong pwedeng pagpilian dito. So we're going to select the scatter. So this is now the representation of this particular graph. So you can select the chart, double click the chart, and then select the curve, and you will notice it has no line. So we're going to put solid line, and we can change the color of the line marker. So we can have here marker option none in order to just show the line of our normal distribution curve. So instead of using this z-score, so we can also have here the value of x and y as a normal distribution. It will not really have a different value. Actually, the representation will be just the same. Or we can use the starting data point of 6.36 and using the interval of 0.005. So in order to have a value of data set. For the value of y, we can directly type the norm. This, so the value of x, the value of mean, the value of the standard deviation, and false. And as I've said, we have 24 data set, and we have a grid of 0.04. So we will have here this particular data. So we're going to put a dollar sign, and this will be the value of our data. So we're going to get back and select a data and add another. So and the curve. So we're going to select the x value and then the y value and click OK. So we have already here the data. So let's change into a solid line and change the color. Let's say color blue. And the marker. So let's have a none. So you can see here that either of the two, you will have the same normal distribution curve. We're already done using Excel applying simple statistics. So getting back with our discussion, so we were able to use Excel calculation in applying simple statistics. So we were able to plot the histogram and normal distribution curve as one graphical representation. So you have to take note that the population standard deviation is a parameter, which is a fixed value calculated from every individual in the population. A sample standard deviation is a statistic. So this means that it is calculated from only some of the individuals in the population. Least squares regression. So the simplest example of a least squares approximation is fitting a straight line to a set of paired observation. So for example, we have set of paired observation of x sub 1, y sub 1, and then x sub 2, y sub 2, and so on until you have the value of x sub n and y sub n. So the mathematical expression for the straight line is this particular equation, equation 17.18. So y is equals to a sub 0 plus a sub 1 x plus e. So a sub 0 is simply the constant and a sub 1 is simply the coefficient of x. So this is simply represented in this particular matter. And you have to take note, class, a sub 0 and a sub 1 are coefficient representing the intercept and the slope respectively, and e is the error or residual between the model and the observations, which can be represented by rearranging this particular equation. We will have the equation 17.1b. Error is equals to y minus a sub 0 minus a sub 1 x. Thus, the error or residual is the discrepancy between the true value of y and the approximate value of a sub 0 plus a sub 1 x, predicted by the linear equation. So, criteria for a best fit. So, one strategy for fitting a best fit line or the best line through the data would be to minimize the sum of the residual errors for the available dataset as in equation 17.2, where n is the total number of points. However, this is an inadequate criterion as illustrated in 17.2a, which depicts the fit of a straight line to 2 points. So we have here the figure 17.2 or the examples of some criteria for best fit that are inadequate for regression. So obviously, the best fit in the line connecting the point, however, any straight line passing through the midpoint of the connecting line, except a perfectly vertical line, results in a minimum value of the equation 17.2 equal to 0 because the errors cancel. So therefore, another logical criterion might be to minimize the sum of the absolute values of the discrepancies, as in the summation, the absolute value of a sub I from I equals to 1 to n is equals to the summation of the absolute value of y sub I minus a sub 0 minus a sub 1 x sub I from I equals to 1 to n. So let's get back to the presented. So we have here the figure 17.2. So this is an example of some criteria for best fit that are inadequate for regression. So in this particular figure, in figure A, this has a 2-point value and it minimizes the sum of the residuals. So in figure 17.2b, this demonstrates why this criterion is also inadequate for the 4 points shown. So any straight line falling within the dashed line will minimize the sum of the absolute value. Thus, this criterion also does not yield a unique best fit. So, a third strategy for fitting a best line is to minimax criterion. In this technique, the line is chosen that minimizes the maximum distance that an individual point falls from the line. So, as depicted in figure 17.2c, so this strategy is ill-suited for regression because it gives undue influence of an outlier. That is a single point with a large error. It should be noted that the minimax principle is sometimes well-suited for fitting a simple function to a complicated function. So, a strategy that overcomes the shortcomings of the aforementioned approaches is to minimize the sum of the squares of the residuals between the measured y and the y calculated with linear model. So, we have here the equation 17.3. So, S sub r, or the sum of squares of the residual, is equals to the summation of e sub I squared from I equals to 1 to n, which is also equal to the summation of y sub I measured minus the y sub I model squared from I equals to 1 to n is also equals to the summation of the difference of y sub I minus a sub 0 minus a sub 1 x sub I squared from I equals to 1 to n. So this criterion has a number of advantages, including the fact that it yields a unique line for a given dataset. So before discussing these properties, we will present a technique for determining the value of a sub 0 and a sub 1 to minimize the equations 17.3. Determine the values for a sub 0 and a sub 1. So equation 17.3 is differentiated with respect to each coefficient. So this will be represented as Note that we have simplified the summation symbol unless otherwise indicated. All summation are from I equals to 1 to n. So setting these derivatives equal to 0 will result in the minimum S sub r. So if this is done, the equation can be expressed as 0 is equals to the summation of y sub I minus the summation of a sub 0 minus the summation of a sub 1 x sub I, and also 0 is equals to the summation y sub I x sub I minus the summation of a sub 0 x sub I minus the summation of a sub 1 x sub I squared. Now, realizing that the summation of a sub 0 is equals to n a sub 0, we can express the equation as a set of two simultaneous linear equation with the two unknowns a sub 0 and a sub 1. So, n a sub 0 plus the summation of x sub I, a sub 1 equals to the summation of y sub I, and for equation 17.5, the summation of x sub I, a sub 0 plus the summation of x sub I squared, a sub 1 equals to the summation of the product x sub I and y sub I. So these are called the normal equation. They can be solved simultaneously as presented in equation 17.6. A sub 1 is equals to n multiplied by the summation of the product x sub I, y sub I minus the summation of x sub I times the summation of y sub I all over n times the summation of x sub I squared minus the squared of the summation x sub I. This result can be used in conjunction with equation 17.4 to solve a sub 0 is equals to arithmetic mean of y minus a sub 1 arithmetic mean of x. So, bar y and bar x are the means of the x and y respectively. So, in order to clearly understand the least square feet of a straight line, so we will have an example. So, for example number 2, so the least square feet of a straight line is called the linear regression. The problem is statement. Fit a straight line to the x and y values in the first two columns of the table 17.1. The solution, the following quantities can be computed. N is equals to 7. The summation of the product x sub I and y sub I is equals to 119.5. Summation of the square of x sub I is equals to 140. The summation of x sub I equals to 28. Arithmetic mean is 4. Summation of y sub I is equals to 24. The arithmetic mean of y is equals to 3.428571. And using the equation 17.6 and 17.7 in order to find the value of a sub 1 and a sub 0. So substituting, so from the given equation, substituting the values, we will have the value of a sub 1 as 0.8392857 and a sub 0 as 0.0714285. So where does this particular values came from? So these are from the table 17.1. So this is the computation for an error analysis of linear feet. So the only given data here of x sub I and y sub I and are all calculated values. So therefore the least square feet is y is equals to 0.0714285 plus 0.8392857 x. To clearly understand the example for linear regression, so let's try using Excel applying linear regression. Continuing with our discussion, so we have here Excel calculation applying linear regression. So actually the given data set or the given points or data set from the table 17.1 which shows the computation of the error analysis of the linear feet are only this particular data set. And the very important equations or formulas that you need to be familiarized with is simply the formula in finding a sub 0 and formula finding a sub 1 in order to find the equation that shows the best fit line for a linear regression. So we will have here first the summations. So let's put the summation in finding the summation of x sub I and also the summation of y sub I. Take note class, I is simply part of the summation equation from I equals to 1 to n equals to 7. So we already have the value of n which will be used in finding a sub 1. We calculated the summation of x sub I and y sub I. We're going to use them in the following calculation. So, finding a sub 0 is using the arithmetic mean of y and the arithmetic mean of x and also the value of a sub 1. So, the value of a sub 1 which has this particular formula. In order to have an equation that represents the best fit line of this particular data set of points. So, first, we have here the a sub 1. So, for a sub 1, we need to have first the value of n, so equals to 7. Take note, class, that it just so happened that the value of x sub I is same with the number of data points that we have. So, class, it doesn't necessarily mean that the value of x sub I is also the same with the value of i's from 1 to 7. For arithmetic mean, so this will be the summation divided by the number of data set, and for the arithmetic mean y divided by the number of set. Or we can also calculate them using the given data points by simply finding the average of the given data points for x and same with the data points given for the value of y. So it just shows the same value of arithmetic mean x and arithmetic mean y. So for the next part, so let's first find the part at the numerator in finding a sub 1. So we already have the value of n. What we don't have is the summation of the product of x sub I, y sub I. So we need to find first the product of each data point and find the summation product of x sub I and y sub I. So we already have this particular value. Take note, class, this particular equation or term is the summation of the squared of x sub I. So you need first to find the value of the squared of x sub I for all the data points from 1 to 7 and find the summation. And this particular summation is the value of the summation of x sub I squared. And squared of summation x sub I is squared the value of the summation x sub I. So continuing, let's now find the value of a sub 1 and a sub 0. So for a sub 1, so at the numerator, we have here n multiplied by the summation of the product x sub I minus the summation of and the summation of y sub I all over n multiplied by the summation of the squared minus the square of summation x sub I. So when you're going to square the value. So we will have here the value of 0.839285714. And for a sub 0, so using arithmetic mean value of y minus the value of a sub 1 multiplied by the arithmetic mean of x. So we now already have the value of a sub 1 and a sub 0. So we can now rewrite y is equals to a sub 0 plus a sub 1 x. So this is the equation of our best fit line. So before we find the best fit line of this particular given data set, so let's plot this out graphically. So let's try to rewrite the given data point. So from this given data point, so dito lang siya galing, class. So we're going to select and insert and select the scatter. So in this particular chart, class, you will notice that this particular chart represents these given data points. So, paano ba natin aalamin yung ating magiging best fit line of this particular data points? So, we will have here the new value of y sub I because we already find the best fit line equation and we also have the series of the given values for x sub I. So, it will be a sub 0 plus a sub 1 multiplied by the value of x sub I. And applying dollar sign. So, applying this particular equation in order to find the new value of y sub I using the given values of x sub I, we will now have here particular new values. So, what we're going to do next is to plot the new values of y in order to really show that this particular equations is really the equation for the least squares fit or the best fit line for linear regression. Select this chart and click chart design and select data. So we're going to add and this will be the best fit line. So select the value of x, select the value of y, so the new y, and click OK. And upon clicking OK, you will see here that it is now plotted directly upon adding the dataset to the chart. And in order to clearly see this chart, so double click the chart and select the data points and click solid line and change the color to same color or similar color ng ating best fit data points. So we already proved and we already show in this particular chart that this particular equation is really the best fit line equation for linear regression. So that is how you find or you apply this particular formula in order to find the best fit line equation, applying linear regression. So getting back with our discussion, so you will notice we still didn't find these particular values because class, this particular value is already part in finding the standard deviation and the standard error of the estimate of the given data set. Quantification of error of linear regression. The analogy can be extended further for cases where 1. The spread of the points around the line is of similar magnitude along the entire range of the data, and 2. The distribution of these points above the line is normal. It can be demonstrated that if these criteria are met, least squares regression will provide the best, that is the most likely estimates of A sub 0 and A sub 1 according to Draper and Smith 1981. This is called the maximum likelihood principle in statistics. In addition, if these criteria are met, a standard deviation for the regression line can be determined as this particular equation, equation 17.9, whereas sub y over x is called the standard error of the estimate. The subscript notation on y over x designates that the error is for a predicted value of y corresponding to a particular value of x. Also, notice that we divide by n minus 2 because two data-derived estimate, A sub 0 and A sub 1, were used to compute S sub r. Thus, we have lost 2 degrees of freedom. Another justification for dividing by n minus 2 is that there is no such thing as the spread of data around straight line connecting 2 points. Thus, for the case where n is equals to 2, equation 17.9 yields a meaningless result of infinity. Just as was the case with the standard deviation, the standard error of the estimate quantifies the spread of the data. However, S sub y over x quantifies the spread around the regression line as shown in figure 17.4b, in contrast with the original standard deviation S sub y that quantified the spread around the mean, as shown in figure 17.4a. The above concepts can be used to quantify the goodness of our fit. This is particularly useful for comparison of several regression, as shown in figure 17.5. So this particular figure is an example of linear regression with A has a small residual errors and B has large residual errors. So in this particular figure in A, so you will notice that the data set or the data points are near with the best fit line, while in figure B, some of the data points are far from the best fit line. So therefore, it has large residual errors. To do this, we return to the original data and determine the total sum of the squares around the mean for the dependent variable. In our case, y, as was the case for equation PT 5.3, this quantity is designated as S sub t. So, recalling, S sub t is simply the summation of the difference of y sub I and the arithmetic mean y squared. So, this is the magnitude of the residual error associated with the dependent variable prior to regression. After performing the regression, we can compute S sub r, so the sum of the squares of the residual around the regression line. This characterizes the residual error that remains after the regression. It is therefore sometimes called the unexplained sum of the squares. The difference between the two quantities, the S sub t minus S sub r, quantifies the improvement of error reduction due to describing the data in terms of a straight line rather than as an average value. Because the magnitude of this quantity is scale dependent, the difference is normalized to S sub t to to yield equation 17.10. So r squared is equals to s sub t minus s sub r all over s sub t, wherein r squared is called the coefficient of determination and r is the correlation coefficient. So which is also equals to the square root of r squared. For a perfect fit, s sub r is equals to 0 and r is equals to r squared equals to 1, signifying that the line explains 100% of the variability of the data. For r equals to r squared equals to 0, s sub r is equals to s sub t and the fit represents no improvement. An alternative formulation for r that is more convenient for computer implementation is r is equals to n multiplied by the summation of the product x sub I, y sub I minus the product of the summation of x sub I and summation y sub I all over the square root of n multiplied by the summation of x sub I squared minus the square of the summation x sub I multiplied by the square root of n multiplied by the summation of y sub I squared minus the square of the summation y sub I. So in order to clearly understand the estimation of errors for the linear least squares fit or the estimation of errors for the linear regression, so we'll have here problem statement. So, compute the total standard deviation and the standard error of estimate and the correlation coefficient for the data in table 17.1. If you recall, table 17.1 represents the computation of an error analysis of the linear fit or linear regression. So, for the solution, the summation are performed and presented in table 17.1. So, the standard deviation is equation PT 5.2. S sub y is equals to the square root of 22.7143 all over 7 minus 1 is equals to 1.9457, and the standard error of estimate or the equation 17.9 s sub y over x is equals to the square root of 2.9911 all over 7 minus 2 equals to 0.7735. Thus, because s sub y over x is less than s sub y, the linear regression model has merit. So, the extent of the improvement is quantified by equation 17.10, which will have r squared is equals to 22.7143 minus 2.9911 all over 22.7143 equals to 0.868, or r is equals to square root of 0.868 equals to 0.932. These results indicate that 86.8% of the original uncertainty has been explained by the linear model. So, let's try using Excel in estimation of errors for the linear least squares fit. Okay, in continuation with our discussion, we're now going to use Excel calculation in estimation of errors for the linear least squares fit. So, in example number 3, estimation of errors for the linear least square fit. So, according to the problem statement, we need to calculate the total standard deviation, the standard error of estimate, and the correlation coefficient, and the coefficient of determination as shown in the data of 17.1. So, this is the given data. So, x sub I and y sub I. So, previously, we have calculated the equation in finding the best fit line of the given data set. So, now we're going to find the value of the standard deviation, the standard error of the estimate, the coefficient of the determination, and the coefficient of correlation. S sub y is the square root of s sub t all over n minus 1. So, we need to find the summation of y sub I minus the mean y squared. So, first, I added another column and we're going to find the y sub I minus the arithmetic mean y squared. And same equation on the next data set and find the summation. So, we have here the summation of 22.71429, so on and so forth. For the standard deviation or s sub y, square root of s sub t divided by n is 7 minus 1. So, this is the standard deviation of s sub y. And class, so for the standard deviation, we can also use the Excel Excel function. So stdev and click S. So this is only for sample. And the number. So these are the standard deviation of Y. So select all the value of Y. We will be able to find the same value of the standard deviation. And so for variance, so this will be the square of the standard deviation. Or you can simply use the Excel function. So var sample and select the data set that you're going to find the variance of. They have the same value of variance and also the standard deviation. And stdev is the standard deviation of the sample, and if it has P, it is for the population. Same with the variance. var.s is for the sample variance and var.p is for the population variance. We're going to find the value of the standard error of the estimate. So this will have the summation of squares of the residual. So let's calculate for the y sub I minus a sub 0 minus a sub 1 x sub I squared, simply the e raised to, so this is the square of the residual. So we're now going to find, so y sub I minus a sub 0 minus a sub 1 multiplied by x sub I squared. And dahil hindi mababago yung ating a sub 0 and a sub 1. And same process, so let's just copy it out. So same selected. So just check whether you use the right formula and the right selected cell. And summing it up, we will have the value of 2.9910, so on and so forth. So using this particular data, we will now be able to find the value of the standard error of the estimate. So that will be square root of S sub r, summation of the squares of the residual, all over n. So we have 7 minus 2. So we will have the value of 0.7734. And in this particular data, and we can also use the Excel function instead of the formula. So we also have here STEYX because we are finding the standard error of the estimate of the predicted Y value for each X regression. And select the Y, the known Y, and the known X. So we will have here the same resulted value of the standard error of the estimate. So for the coefficient of the determination, or R squared, finding R squared or the coefficient of determination, so it will be the S sub t minus S sub r divided by S sub t. And it will have a value of 0.8683171. So for the coefficient of correlation, so it will be the square root of the coefficient of determination. Or we can try using the formula n multiplied by the summation of xy minus the product of the summation xy and yi divided by the square root of n multiplied by the summation of x squared minus the summation x square and times the square root of n multiplied by square of I minus the square of, you're going to add another column for the y sub I squared, and you will be able to find the same resulted value of the correlation coefficient. And you can also try the Excel function. So it will be correl and select the array 1 and select the array 2. So you will also have the same value of correlation coefficient and pairing. So you will be able to have the same value of the coefficient of determination. So that is how you apply linear regression using Excel.